Hey everyone, welcome back to another video by Camroom 5. In today's series of video, we're going to start with A2 level chemistry. And we're going to begin with the chapter of further energetics. We're going to start with further energetics, which means we are going to be building up on the concepts of energetics from our first year AS level. We're going to start with the Haber's law. If you remember from the first year AS level, it stated that when a reaction happens, the reactant, when they turn themselves into the product, it could be a single step pathway where they just convert themselves into the product, or it could be a series of steps. For example, they turn themselves into something, then the something, let's say the something is X, then the X turns itself into some other thing. For example, this other thing is Y, then this other thing turns itself into the Z thingy, and then Z makes the exact product as in the first case. So it could be a direct step like this over here, as I'm highlighting with a blue pen. It could be a direct step, or it could be a series of indirect steps like the one I'm highlighting over here, and then it can get the same product. Enthalpy change would still be the same. The enthalpy change H direct would be equal to the sum of the enthalpies 1, 2, 3, 4. So Haber's law can be applied to the formation of ionic compounds in a phenomena known as the Born-Haber cycle. The Born-Haber cycle is a kind of an energy cycle where we talk about how various ionic compounds are made. So imagine you have to make sodium chloride, which is the ionic compound. The general equation, the overall reaction has to be solid sodium reacts with half mole chlorine gas to make sodium chloride in the solid state. Solid sodium is the element and chlorine is the element because you need one atom of chlorine, right? You don't need two atoms. And then you finally get sodium chloride in the solid state. This is the enthalpy of formation for sodium chloride. But actually this reaction doesn't happen directly. It has multiple steps associated with it. So in this video, we will be talking about each step and how it happens. Actually, what happens is that when sodium solid reacts with half mole chlorine gas, you do not get the sodium chloride solid directly. It has multiple steps associated with it. We will be talking about each step and whether they are exothermic or endothermic to try and create a Born-Haber cycle. For each endothermic process, I will be moving the arrow upwards. So in the first step, what happens is that sodium, which is solid, turns itself into sodium gaseous atoms, while the chlorine exactly remains the same way. This phenomena where solid sodium turns itself into the gaseous sodium is known as enthalpy for atomization for sodium. I will be using this sheet for definitions because there are going to be some new definitions that come across. So first definition that we came across was enthalpy for atomization. Let's define it. It is the energy change, because it's a kind of enthalpy, so it's the energy change when 1 mole of gaseous isolated atoms, I repeat, 1 mole of gaseous isolated atoms are created or formed from their element in their standard state. So you're making 1 mole gaseous atoms from the element in their standard state, at standard conditions. I will keep writing STD for standard conditions. Guys, just please excuse me over here, okay? It's neither what you're thinking, it's nor save the date. its standard conditions. So here what happened was that sodium was solid. It converted itself into gaseous atoms, and that was enthalpy for atomization for solid sodium. It is an endothermic reaction. You should remember it's an endothermic reaction because you are converting solid into gas. So it's a kind of endothermic process. Once the solid sodium is turned into gaseous sodium atoms, the next step happens is that sodium turns into ions. So sodium atoms are turned into ions. So now it looks like that sodium gaseous atoms become sodium cations. They lose their electron and half mole chlorine gas is still the same. We will call it ionization energy as we have already studied in AS level. This is known as first ionization energy for none other than sodium. We know the definition for ionization energy, so the second step was enthalpy for first ionization energy for sodium or any other thing. We have already discussed the definition in AS level, so I'm not writing that. Here sodium gaseous atoms gained energy, became gaseous positive ions, lost an electron, and that was it. It's also an endothermic process, so the arrow is still moving upwards. Let me put the entire picture a little lower so that we have more space in the upward direction. Now what happens next is you look at chlorine. When you look at chlorine, you realize that you have diatomic molecules. You don't need that, you need atoms. So you will atomize the chlorine molecules to make individual chlorine atoms. The lost electron is still the same way. The sodium gaseous ions are still the same way. This is known as enthalpy for atomization for 1 mole chlorine, and that is also an endothermic process. So far we have done 3 processes which are all endothermic. First was the atomization of sodium, then we ionized the sodium, and then we atomized the chlorine. Now next step is going to be chlorine gaining the electron, and that is known as electron affinity. Let's define it. It is the energy change when 1 mole gaseous atoms each gain an electron to form a negative ion at standard conditions. So here you are making the chlorine gain electron. Chlorine atoms were gaseous. They gained an electron and now they are chloride gaseous ions. Here basically the process is exothermic. Now you can ask why. Basically, if you imagine the atom of chlorine, this is the nucleus, this is the electronic shells of, let's suppose, chlorine. This is the chlorine. Here we have the protons from chlorine, and there's an electron which has to be gained. There is an attraction between the nucleus of chlorine atom and the incoming electron. This is the incoming electron, and this is the nucleus of our atom, of, let's suppose, any atom. So when the attractive forces are there and electron is gained, energy is released. So it's an exothermic process. It's not endothermic, it's exothermic. So for electron affinity, we will make the arrow move downwards. It will look something like this. It will move downwards. Now sodium positive is still there. The electron is no more there because it's gained by chlorine atoms to make chloride ions. Now you can see we are ready with sodium ions and chloride ions. What should be the last step? The last step is making a lattice, which is immensely exothermic. Let's label the previous one, by the way. It was the electron affinity for chlorine, which was an exothermic process. The last one is known as lattice enthalpy for sodium chloride, where both the ions combine and you can get sodium chloride ionic lattice. So your products are going to be sodium chloride ionic lattice. Let's define this also. The fourth definition for today is enthalpy for lattice, or you can say standard enthalpy for lattice. It is the energy change. I'm not changing the color right now. It's the energy change when 1 mole, no more no less, when 1 mole ionic lattice, 1 mole ionic lattice is made from its gaseous ions, at standard conditions. When 1 mole ionic lattice is made from its gaseous ions at standard conditions. So the equation can look something like this. Sodium ions were in the gaseous state. Chloride were also in the gaseous state. Now they made sodium chloride lattice. It will be an exothermic process because ions are coming together. You can see as a big picture, if I somehow make it smaller, you can see the starting level is not the same as the ending level. Why is that the case? Because there is a net change. There is a net change, and that is equal to the enthalpy for formation. Enthalpy for formation for sodium chloride. So this way, if I put a line over here, this way you should be able to see that enthalpy formation is the net step. It is the net change. And enthalpy formation of sodium chloride is equal to the sum of all the other enthalpies, which includes atomization of your metal like sodium, then ionization energy of your metal, which is sodium, then atomization of your non-metal, which is chlorine, then electron affinity of your non-metal, which is chlorine, and finally making the lattice, which is sodium chloride. So in today's video, we have talked about the idea of the Born-Haber cycle. We did the example of sodium chloride, and we did some important definitions over here. In the next video, we'll do some more questions. Stay tuned, guys. Thanks.